so we are looking at section 3.5 today, solving nonlinear systems. So we have seen linear systems before, where we are solving to find where two lines intersect, or we've even done where things intersect in 3 dimensions. Today we are looking at nonlinear systems. So we have variables that are going to be squared, essentially, in addition to variables that are not squared. So this is in your student journal on page 65. So what I want you to do first here, go ahead and see if you can figure out which systems match. So essentially, whichever one goes with this graph here should have both of those functions graphed on it. So see, go ahead and pause and kind of try your best to match here. When you think you've got it, unpause it, and I'll show you what goes with what here. All right, so the things I'm looking at. First, I know that in the system with A here, y equals x squared is a parabola, and that's just the basic parent function parabola. It opens up, vertex at 0, 0. And then I know the second equation in the system is a line with a positive slope. So when I look through these graphs here, I'm looking for something that has a parabola and a line. Okay, so it couldn't be B, C, or D. Those are 2 parabolas. So it's got to be either A, E, or F. And I said that's the most basic parent function parabola with vertex at 0, 0. It's got to be this capital A here. So this one is capital A. I'm going to go ahead and cross that one out then, so I know that one's accounted for. When I look at system B then, I still have a parabola. And since it's positive, this one opens up. And a line with a positive slope again, because it's a positive x plus 2. So when I look at my options that are left for parabolas with a line, I'm looking at either E or F. All right, and since I know the line has a positive slope, it's got to be E. So 2 has to be E. All right, when I look at C, then this is my last one that has a parabola and a line. So parabola that opens up, line with a negative slope, that's got to be F. All right, the last 3 then are all systems with 2 parabolas in them. And when I look at each of them, I'm looking at the x squared pieces, and they all have 1 positive and 1 negative. So each graph has a parabola that opens up and one that opens down. So that's not going to help me kind of eliminate. What I want to look at, though, is this last piece, the constant. So they all have different constants, and what that constant tells me, remember, is the y-intercept. So I'm looking for 2 parabolas, one that opens up and one that opens down, and the y-intercepts are at 6 and negative 6. That would have to be B here for this one. When I look at system E, then, my y-intercepts are at 1 and negative 1. So that 1 and negative 1, that one has to be C. So then this last one must be D. So my intercepts are at 1 and 2, so that fits as well. So what we're going to be doing here is we're going to be given equations, and we're going to be figuring out where they intersect at. So like, for example, if I were solving this system here on the first one, I'm trying to find the coordinates of this point and this point. Where do they intersect at? So what we want to think about is how many possible solutions are there. So if I'm looking at a parabola with a line, if I had something like this situation, there could be no solution. If I have a parabola and the line goes through it, there are going to be 2 solutions. And it's also possible that if I have a parabola with a line that only touches it once, so think about it, it could like be at the vertex right there, it just touches, then I would only have 1 solution. Okay, so when I'm dealing with a quadratic and a linear, I could either have 0, 1, or 2 solutions. Let's think about 2 parabolas then. So we saw in the last example parabolas that had 2 solutions. It's also possible to have parabolas that never intersect. Something like this would be no solution. It's also possible to get one solution with parabolas if they just touch. Right there. Okay, so when we're solving these systems, we have to keep in mind that I could be ending up with 0, 1, or 2 solutions. All right. Let's go to page 68 now. Okay, so we're going to be solving algebraically here, and they say solve the system by substitution. We're going to be looking at numbers 6 and 8. Okay, so when I look at number 6, I've got a line. The first one is linear. The second one, I have a squared in there, so that's a parabola. So when they say solve by substitution, that means I either want to get x or y by itself, and then I'm substituting it into the other equation. Well, this one is already set up for substitution. Y is already by itself. So I'm going to take what y is equal to and plug it in for y. So this y here now becomes x plus 4. So we have x plus 4 plus x plus 2 squared plus 1. Okay? So now to solve this, I've got x's on both sides here. I need to simplify that some. So I'm actually going to break this down some. So when I'm squaring something, that just means I'm multiplying it by itself. So x plus 2 times x plus 2, and I'm going to expand on that or multiply or distribute. So I'm going to have x squared plus 2x plus 2x plus 4 plus 1. So I'm just going to simplify that right side some then. So x squared plus 4x plus 5. Okay. So now what I want to do, I have a quadratic that I'm solving. I want it to be equal to 0. Okay, so I'm going to subtract 4, subtract x. Okay, to see what my options are here. So I would have 0 equals x squared plus 3x plus 1. So my first choice is to always factor, just because it has the least amount of steps. Once you get it factored, you just set each piece equal to 0. But I'm looking at this here. There's no way that I'm going to be able to factor this. Nothing, or the only thing that would multiply to be 1 is 1 and 1. And there's no way those are ever going to combine to give me 3. So I would want to think about something like completing the square or using the quadratic formula. We could very well complete the square here. So my middle piece is a 3. So I could cut 3 in half and get 1 1/2 m squared. So if you want to work with the fractions, that's fine. I think I'm going to do quadratic formula for this one. So just setting up the quadratic formula, opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. Negative 3 plus or minus, let's see what's under that square root. 3 squared is 9. 4 times 1 times 1 is still 4. All over 2. So negative 3 plus or minus the square root of 5 over 2. So that's as simple as that one's going to get, right? We can't break down the square root of 5 at all. So this is what x is equal to. So there are actually two x values here. There's negative 3 plus radical 5 over 2 and negative 3 minus radical 5 over 2. So now, remember what we're trying to find is where this line and this parabola intersect at. So it intersects in two different places, and I know that because I have two solutions, the plus radical 5 and the minus radical 5 versions. So what I want to do now, I want to find the y coordinates. So if you look way back up, we originally had y equals x plus 4. And I now know what x is, so I can substitute in what I know x is to solve for y. So I'm going to first look at the positive version here. Okay? So because of that radical, there's not a ton we can do here, but we can simplify this a little bit. So what I'm going to do is I'm going to rewrite 4 to have a common denominator. So to get 4 with a denominator of 2, I would have to think about 4 as being 8 over 2. So now this is negative 3 plus radical 5 plus 8 over 2. And then I can combine that 8 and negative 3 to give me 5 plus radical 5 over 2. So my final answer here should be an ordered pair. They intersect at negative 3 plus radical 5 over 2, comma 5 plus radical 5 over 2. So if you were to find those decimal approximations, that would be where they intersect. So that's the first solution. For the second one, I'm still going to plug into y equals x plus 4, but now I'm going to do the other x coordinate, so the minus version. And same idea, so I'm just going to go ahead and write 4 is 8 over 2, because I know I'm going to need a common denominator to add. Alright, so on top there, I'm going to have 8, and the negative 3 is going to give me 5. This time it's just 5 minus radical 5 over 2. So my coordinate is negative 3 minus radical 5 over 2, because that's what we plugged in to find y. And that gave us a y of 5 minus radical 5 over 2. So our two solutions would be these and the big, nasty, ugly coordinates here. Alright, so that's about as tough as it gets. That's a pretty long one. Let's look at, we're not going to do number 7, but we are going to do number 8 here then. Okay, number 8's not quite as grueling. So when I look at this, I want to solve a substitution, and I've already got y by itself in that second equation. So what I want to do is I want to go ahead and substitute this in for y in the first equation. So 2x squared plus 10x plus 48 equals, now instead of y, I'm going to put whatever y is equal to. So that's negative 4x squared minus 16x, and then don't forget this minus 10y that we have hanging out, or minus 10x we have hanging out at the end there. Okay, so I'm going to try and get everything on one side here to simplify a little bit. So adding 4x squared to start. So I have 6x squared plus 10x plus 48 equals on this side negative 16x, and negative 10x would give me negative 26x. Okay, so I'm almost there. Let's go ahead and make this equal to 0. So adding 26x to each side. So 6x squared plus 36x plus 48 equals 0. So now, I got some pretty big numbers here, but notice that I can get rid of the 6 out in front. These are all things that are divisible by 6. So if I want to get just x squared, if I divide by 6, I would get x squared plus 36 divided by 6 is 6x plus 48 divided by 6 is just 8. It'll just equal to 0. Okay, and then I know this one is going to factor. So I want to think about things that multiply to be 8, 4 and 2. 4 and 2 add to be 6, so that's perfect. Okay, so now I set each piece equal to 0. I have x is negative 2, x is negative 4, and we're almost there. So what we've discovered is there's two solutions. These two parabolas cross each other twice, and we know the x coordinates now. So we have to plug that back in to find the y coordinate. Let me just get rid of some of this here. Alright, so I need an equation for y. So if I look back up, my original equation was y equals negative 4x squared minus 16x. So I'm going to plug in each of those x values. So negative 4 times negative 2 squared minus 16 times negative 2. So that would give me negative 4 times 4 plus 16 times 2 is 32. And negative 16 plus 32, or just 16. So my coordinate pair here is negative 2, comma 16. So that's one answer.